In this video, we're going to talk about quadratic regression, which is a special case of nonlinear regression models. And we're going to use data file Reynolds. So here I have the data file Reynolds. Reynolds is a manufacturing company, like laboratory equipment manufacturing company. And in this data file, for a sample of 15 employees, we have the lengths of employment, the number of months that they've been employed with the company, and also a measure of their performance, the number of electronic scales that they have sold during their employment, right? So now we want to see if there is any relationship between, or what type of relationship exists between the performance and the experience, right? So the number of scales sold and the number of months that they've been employed. We want to see if there's any relationship. So the first thing that we are going to do here is to visualize the relationship. So in order to visualize relationship between two variables, we know that we're supposed to use scatter chart. So I'm going to select these two columns and go to Insert tab and add a scatter chart. So by default, Excel is going to put the first column into the horizontal axis and the second one on the second column on the vertical axis. So that's exactly what we want, because sale for me is a dependent variable is Y, and I want it on my vertical, and month employed, the length of employment or experience on the horizontal axis, and that would act as my independent variable. So I'm going to get rid of the grid lines. I'm going to add the axis titles. So this is sale, scales sold, and here this would be month of employment or month employed. All right, so this is the scatter chart. Now, in order to estimate the relationship, in order to fit a line here, I just need to add a trend line. So if I add a trend line, I'm gonna click on the data points and add trend line. By default, Excel is gonna add a linear trend line. A linear is gonna fit a linear regression, a linear equation, a line here. So if I add equation on top of the chart and R squared, I see that my line here, my linear regression is, I have a positive relationship. The slope is positive. And of course, I can see it here that there is a positive relationship between the experience and sales performance. The R squared, which shows the strength of the relationship, is pretty large, is 79%. So that's great. Let me just make it a little bigger. All right. So that's the linear equation. Now, if you notice, if we just take this line, the trend line, and rotate it and put it in the horizontal axis, we see that most of the points at the left side of this line, at the left side here, are below the curve, below the line. And points at the right side, at the upper side of this line, are below the curve. And most points that are at the middle, they're taking a positive value, positive residual, right? Because residual, remember, is the distance between y and y hat. This is residual. Residual, the distance between y and y hat. Residual for this one is negative, for this one is positive. Positive, positive. So for most points in the middle range, the residual is positive. The residual in the left and right side of the experimental range is negative. The residual is negative, y minus y hat, negative, positive, negative. So that indicates, that can be a sign that a linear regression is not necessarily the best model. There might be a non-linear, in this case, a quadratic model that is better than this. So what I'm gonna do now, I'm gonna change my chart. I'm gonna change my trend line type. Instead of a linear, Excel provides us with a few options, but I'm gonna go with polynomial with the second order. And you can see here, I'm just gonna focus on polynomial here. We're not gonna really make it too complicated. You see the R squared with second order, the R squared jumped from 79% to 90%, which is a very significant change. And when you look at the line here, it's a much better fit than the linear equation. Just compare it again. If I click on the linear trend, 79, and again, most point in the middle are above, below, below. That's not good. That's just underestimating. That it's actually overestimating here and here and underestimating at this range. That's not good. We want it to be actually always randomly distributed, symmetrically distributed. So again, if I go with polynomial with the second order, that's quadratic. That's quadratic regression. You see now it's actually predicting the relationship between sales and performance and experience much better and much cleaner, right? And R squared, now you see that jumped by 11%. So this shows that this model has a better ability in terms of predicting the performance, right? I'm just gonna, let me just go ahead and do this. Now, this is a little bit more complicated than the linear model. As you can see here, in the linear model, we just had one x. Now we have an x squared, an additional factor. So this is, we call it quadratic, and now it's actually a multiple regression with x and x squared as our independent variables in the model, right? Which is a more complicated model. If I add to the order of my polynomial, right, instead of quadratic, if I go with the cubic model by adding the order by 1 unit, I'm sure that the model is going to be more complicated. R squared is going to go up, but is it worth it or not? So let's just try to add the order by 1 unit. So now we see that the R squared went from 90% to 91%. And now the model is much more complicated. We have the order of 3. Now let me just click again, add the order to 4. And you see it jumped from 90% to 91%, R squared, not adjusted R squared. Usually for comparison, we should look at the adjusted R squared, but R squared also gives us a rough estimate of the strength. Let's just go with 4. 90, it was 91.25, now 91.89. You see that this the jump is now smaller. And if I go from 4 to 5, 91.9, now 91.97, like 0.07% increase. And if I go from 5 to 6, again, the increase in the R squared is much smaller. The model is getting crazy, like much more complicated. This is a very lengthy model with not much of increase. So in quadratic, from quadratic to here, what happens is that my R squared went up by almost 2%. So if I just decrease it back to 2, you see 90%, and by 6, 92%. So just 2% in R squared, but now I have 6 independent variables rather than 1, rather than 2, right? So 4 more independent variables. So now among this one, a polynomial with the 6th order and polynomial with the 2nd order, which one is more preferred? We know that when you want to pick a model, it's not just about R squared. So you should look at the adjusted R squared. That's one thing. The second factor that is important is the simplicity of the model. You want to have a simple model with all the variables significant, with all the independent variables, all the variables that are in the model, you want them to be significant. I bet that most of these factors are not significant. I mean, this doesn't allow us to check, but if you check, some of these will not be significant. And again, the change in R squared is not huge. We don't have the adjusted R squared, but even R squared, by adding 4 more independent variables, by making it much more complicated, you're just getting 2% more explanation of the total variation, which is not really great, which is not really enough, all right? This one, so that's one thing. The problem with more complicated model is that while they the problem is called overfitting, which means that while they make the model more and more accurate within your sample, if you want to test it, if you want to use your model on an external data point, if you want to use it for prediction for an external employee that is not in the sample, when you have a more complicated model with more number of independent variables, the model that is overfit is not able to make accurate prediction. Usually the simpler models are better in terms of external prediction when you use it for the data points that are not necessarily in your sample. For external prediction, usually simpler model works better. And in practice, we value simplicity. We look for simpler model. So that's that's basically what we need to do. So in this case, I'm just going to go with 2nd order polynomial or quadratic regression. So this is what we see here. Now, before we go ahead and run the regression tool and get the p-values, I'd like to ask you one question here. What is the implication of having, what does it mean? So before we knew we had just one slope and one y-intercept, and we knew how to interpret those. Like slope was the rate of change in y with respect to one additional 1 unit increase in x, for example, right? So that's how we define slope. But how about here? So what do we get from these numbers? Just think about it. Just maybe pause the video, think about this one. A quadratic relationship tell us that the relationship is not constant. You don't have a constant increasing or decreasing relationship within your experimental region. All right. So they mean that the rate of change is now variable. The rate of change is not constant. The rate of change is variable. And when you have a graph like this, it means that there is a best month of employment. There is a best range for which you get the maximum sales scales sold for employment. And as the month employed increases and increases and increases, you should expect that these sales go down a little bit, which means that there is a best range of X in terms of the maximum Y, right? So that's really the meaning of it. That means there is a best range, and that's so these rate of change in Y is decreasing, 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 and at some point it gets constant. So it doesn't change if you increase month of employment a little bit. The sales does not increase the performance. But then again, after some month of employment, it starts declining. All right, so that's just the implication of having a quadratic, which means that we have now a best or worst range for the independent variable. All right, which usually in that case, minimum and maximum happen. So this is a quadratic regression. Now, what do we do? How do we get the p-values and stuff like that? Scatter charts do not provide us with p-values. We don't get adjusted R-squared and stuff like that. So how do we get those? We need to use the regression tool. So for the regression tool, this is my X, this is my Y, all right? X range, Y range. I also need, for quadratic regression, I also need an X squared. So what I'm gonna do, let me just take it here. What I'm gonna do, I'm gonna insert one cell. This is very important. You wanna insert one cell next to your X. So I have my X month employed, and I'm gonna add another one, month squared, as my X squared. X is a month, X squared, month squared. And it's simply squares of month. So just, for example, at B2, I have the formula is A2 squared, and I just drag it down just to make sure that I get the same. I get quadratic, I get month squared basically, right? So now I have X squared, and Y. I'm just gonna highlight my Y just so I know that this is my Y range. All right. If I run the data analysis and regression tool, so Y range is going to be the scales sold. X range is going to be month and month squared. Labels, and put it in the same sheet. And I'm going to check for residual plots just to see how residual plots are looking like. All right, so okay. So I have the residual plots here. As you can see, they're pretty nice. They just show all the conditions that we were looking for. They show both of them. They show symmetrically distributed residuals around zero with a constant variance. This one also is okay. I mean, I have a small sample, but that's fine. So the residuals are good. I'm just gonna write down the equation. Equation is gonna be exactly the same as my quadratic regression equation that I got from scatter chart. So it's gonna be sales equals 61.4243 plus 5.8198 month plus the coefficient for month squared minus 0.031 times month squared. So that's the equation, and it's exactly the same as the quadratic equation that we had using the scatter chart, right? Checking the p-values. Both p-values, residual plots are fine. Both p-values are less than 5%. Of course, there is multi-collinearity between x and x squared. Between month and month squared. Of course, if you find the correlation, it's going to be correlation of month squared, month and month squared. It's 97%. But that's not a problem because p-value, both p-values are less than 5%. Even though multi-collinearity exists, which we knew it, since p-values are less than 5%, that's not a problem, right? So we have, and then adjusted R squared is 88%, and R squared 90. R squared should be exactly the same as what we had, 90% point 13, 13%, right? So this is how we get this. I'm just thinking, is there anything else? Let me just get to the slide here. So in general, the quadratic regression line looks like this. So the y hat is equal to the estimated value of y, the dependent variable, is equal to b0 plus b1x plus b2x squared, and there shouldn't be any residual because this is the estimated value, right? So yes, and then more important than this one is this graph. When the coefficient for x squared is positive, it means that we have a relationship like this. So in this case, we have a range in which, a range of x in which minimum of y happens. And when B2 or beta 2 is negative, we have a downward quadratic curve, which means that there is going to be a range for which the maximum of y happens. So example of this one would be the amount of basically, or the distance that people can run in 10 minutes with respect. So that if we take that as y, the distance that people can run as y, and then x as their age. So if you just take it from age of 5 to 100, the curve is going to look like this. So there is going to be after 5 or like 5, 6, 7, the best range probably is going to be between maybe 15 all the way to 25 or 30. And then after that, it's going to be declining.